Hello, everyone. Welcome to CBRS Has Arrived. This is a joint presentation with Celona and iBwave. Today, we'll be discussing a real-life CBRS case study, how to design for CBRS networks, and doing a demo of an example project for designing an indoor small cell network. I am Andrew Nagy, Director of Solutions Engineering. Hello, everyone. You may recognize me from my experience in the Wi-Fi industry and with enterprise networking, and from my site, revolutionwifi.net. Also with us today, we have Djamel Ramoul, who is a sales engineer with iBwave, and will be walking you through a design demo with a case study project. So with that, let's get into our topic for today. I'm going to be covering a design overview and aspects for private LTE networks. Just some high-level background information on private LTE to start us off today. LTE and the CBRS band offer interference-free operation that is less congested than typical unlicensed spectrum. It's secure by default, so offering high level of security for connected wireless devices. It offers service level objectives for mission critical applications that can guarantee reliability, including bandwidth and latency for applications within an enterprise environment. Provides infrastructure control for mobility and traffic of client devices, and provides very high performance at range given the high power for outdoor installations and some technical characteristics with the LTE protocol. When you're looking at designing a private LTE network, there are some considerations you need to think about. These include enterprise network integration, private LTE RF design factors, and we'll be going through an actual RF design demo with facility modeling and heat mapping. So on the enterprise network integration side, it's important to prepare the network with cabling, switching, and routing, since a private LTE network integrates directly with an enterprise wired and wireless network. This includes security, segmentation, and IP addressing, and determining where to deploy the enterprise packet core, whether in a physical or a virtual form factor. On the RF side, you need to look at spectrum availability, since spectrum in the CBRS band is tied to the geolocation of the site and must be registered with Spectrum Access System database providers. We also want to look at coverage and capacity requirements to meet our customer needs. And we'll look at specific LTE RF design metrics and how we should design for LTE networks for received signal power, signal to interference and noise ratio, interference handling, and the TDD, or time division duplexing configuration, which will help us weight uplink versus downlink traffic. So looking at private mobile networks in the enterprise, it might be just helpful to look at what a sample architecture might look like. This typically involves indoor or outdoor access points, which may also be called small cells or CBSDs, that are deployed throughout the environment that connect back to an enterprise packet core. This packet core can reside either locally on site, or it can be deployed centrally in a private data center or a private or public cloud environment. Some key characteristics of these networks are that the access points are plug and play with an existing access layer network and switching environment. They provide SAS registration and dynamic RF management to automate the optimization of channel and power planning. User traffic is tunneled back to the packet core, similar to an existing Wi-Fi controller environment that can then integrate with existing customer networks for VLANs or VXLAN integration for customer IP addressing on the network. Typically, there's also a unified operations and management dashboard in the cloud for these types of solutions. And finally, a key characteristic of private mobile networks are the integrated QoS and service level objectives that we can provide to enterprise devices and applications to provide them with granular policies for QoS, service reliability, and KPI reporting. When we begin designing a CBRS network, it's important to understand the different access point categories, or CBSD categories, as that will influence how we design these networks and what requirements are in place for SAS registration. Category A are the lower power, typically indoor deployed access points that are limited to 30 dBm EIRP per 10 megahertz of spectrum. If these are deployed indoor, there is no CPI requirement, which is Certified Professional Installer, when these devices are auto-located through GPS. If they are deployed outdoors, they are restricted to less than 6 meters height above average terrain and will require a certified professional installer to sign off on the installation parameters. Those include exact positioning of the radio for database registration and power and antenna orientation to ensure that the information in the database is accurate. Category B CBSDs, on the other hand, are higher power and deployed outdoor only. They can operate up to 47 dBm EIRP, which is 50 watts of power, and a certified professional installer is always required to sign off on those installation details because of the higher risk for interference to incumbents in the band. The accuracy for the geolocation and the placement and when registering with the SAS is plus or minus 50 meters horizontal and 3 meters in elevation. So when you begin coverage and capacity planning for a CBRS network, it's important to understand what parameters you need to plan for. First is every radio is tied to a specific geolocation for spectrum availability. You will begin planning your coverage area based on the facility type, either indoor or outdoor, as well as the propagation characteristics of that environment to understand how many APs you'll need from a basic coverage perspective. Moving on, then you'll start layering in application and user density requirements to understand the capacity on the network, and you may require additional radios than you did for pure coverage-based planning. This can all be automated with the Celona Network Planner that's available for free on the web. This allows you to input specific geolocation parameters, identify what spectrum is available, and put in your coverage and capacity requirements to start budgeting and planning for a new project. This is very useful at the beginning of a project to set budgets and start estimating a bill of materials for ordering and planning engineering resources throughout the project. Next, I'd like to talk about a few design factors for private LTE, since these do differ from what you may be used to with Wi-Fi networks. The key characteristics that you're going to be designing for are RSRP, which is the receive power, SINR, which is the signal to interference and noise ratio, and what TDD configuration you're going to have specified for uplink and downlink weighting of traffic. First, RSRP is the reference signal receive power, and this is the receive power specific to a serving cell or an access point. And it is measured on a single antenna on a single subcarrier of 15 kilohertz spectrum in order to identify the cell with the strongest signal in any given location. This is different from RSSI or receive power in aggregate, which measures receive power from all sources within the environment and all energy received from LTE base stations or access points. So it's very important to plan for RSRP rather than receive power. SINR is signal to interference and noise ratio. This is not only the difference between the desired signal source and the underlying thermal noise floor, but also the interference ratio from other access points in the environment. This is also specific to the serving cell, and it's really that delta between the desired cell signal and the interference and noise ratio. And finally, the TDD configuration schedules LTE radio resources for uplink versus downlink traffic. This is a static assignment, and there are various configuration profiles available. And you will set this for a given site or facility so that all the access points match their configuration, which is very important for interference handling. So a little bit deeper dive into each of these. Let's start off with the physical layer of time division duplexing LTE. And the key here is to understand that LTE uses OFDMA in the downlink direction, and each subcarrier is 15 kilohertz wide. The 15 kilohertz subcarrier width is very important when we're looking at those RSRP and coverage characteristics. So when we look at RSRP, those reference signals in the OFDMA time space are sent within the physical resource blocks on very specific tones or subcarriers at specified intervals throughout the transmission. Those are sent on a single subcarrier at 15 kilohertz wide, and that is what we're measuring the signal strength on. That is also very important to understand when we get to SINR and the noise floor on a 15 kilohertz subcarrier. When you're designing a network, you're going to look at typical range of values for RSRP from neg 60 dBm as a very strong signal, all the way down to neg 120 dBm, which would be the cell edge where the noise floor typically is at. And you'll be designing for most capacity-oriented networks somewhere between neg 90 to neg 95 dBm as a typical design target to have throughout an environment. This may vary depending on the project specifics and requirements, however. SINR is the next very important characteristic to design for with LTE. The thermal noise floor, again, is due to the 15 kilohertz subcarrier width, because the thermal noise floor is derived from white noise, and it's dependent on the temperature in the ambient environment as well as the bandwidth that we're measuring it on. So it's very important that we understand that we're measuring only on a 15 kilohertz subcarrier. Typically, that results in around a neg 130 to 131 dBm thermal noise floor. Then we add in the noise figure from the receiver device, and this is degradation of signal due to the receiver componentry. It's common to have about a 6 dB noise figure within common modern electronics, and so we'll see the noise floor potentially be somewhere in the neg 125 dBm range for a common LTE client. Finally, we want to talk about interference and how that impacts SINR. When multiple access points are deployed within an environment, some of them may end up being deployed on the same channel or frequency. In this case, LTE uses inter-cell interference coordination to ensure minimal interference between those access point transmissions, as well as the client transmissions within those cells as well. So LTE schedules traffic to avoid interference. So when the LTE scheduler is scheduling both downlink and uplink, it will try to interleave those schedules, those transmissions between access points and clients within the adjacent cells. This works across multiple cells or APs, and those APs exchange interference indicators at regular intervals. The interference impacts the neighboring cells' SINR if they cannot be scheduled on different time slots. It's important to note that LTE interference is non-blocking. Unlike Wi-Fi, where it's a back-off and contention-based protocol, two LTE access points or clients can transmit at the same time, and it impacts the noise floor, but parallel transmission is still possible. So there might be a slight degradation in the SINR and the resulting modulation in data rate for those transmissions, depending on the severity of those cell overlap and interference noise. But those transmissions can still occur simultaneously. And this is where it's important to have a common TDD configuration for uplink versus downlink frame scheduling, because you want your access points and clients to both be on downlink or uplink across cells at the same time, so that interference handling and coordination can be most effective. There are multiple different TDD frame configurations for LTE in the CBRS band. Only two of them are allowed at this point, however. Configuration 1, which weights upload to download from a subframe configuration evenly, and config 2, which provides higher weight to download traffic. So with that, I will hand it over to Djamel to go through a RF design demo using iBwave design. Djamel, over to you.
Thank you, Andrew. Found it really interesting from someone who's coming from Wi-Fi background to explain LTE like this. Really good job. Hi, everyone. Djamel Ramoul, sales engineer at iBwave. Been in the wireless industry for 15 years. Done many LTE design, small cell design in the past using the iBwave software. So today I'll try to show you a demo of how you can design a CBRS network using the iBwave design software. I have with me a sample file of a hotel that we did model in 3D. We have all the walls and we have all the floor plans, and let's show you how to design a CBRS network, some basics. I'm going to switch to my screen. Okay, this is a sample file of a hotel, and you can see I have 4 floors. First floor, second floor, third floor, and fourth floor. I have the roof. And I'm just going to start with the first floor to show you how you can do a design. Well, after modeling the building, loading the floor plan, and if you have the CAD drawing, it's easy to model the walls. And once you have the building model, what you need to do is to start loading some small cells, right? It might be called CBSD in the CBRS world. Maybe it's called LTE AP. In iBwave, it's under the signal source subcategory small cell. So when you go there, it will load the database, and you would see different manufacturers. Then you could browse and go to Celona, and I have some models from Celona. I'm gonna just use that one. And before dropping the small cell, you could define some parameters. Let's say what is the band. So in LTE, we want to use band 48 for CBRS. You could use 10 megahertz or 20 megahertz, depending on what is available in that area. Can I use many channels? Will the SAS allow me to use 20 megahertz channel or only have one channel, 10 megahertz channel? Let's assume it's the worst case scenario and I only have one 10 megahertz channel because I didn't bid, I don't have any PAL license, or just general license. But if I do have, I know what are my channels, then I could select, if I have 2, I could select 20, and then I could select the channel number. So here I could go to the list of channel number and select the ERFCN that I'm going to use. I could also add the cell ID and PCI, which is another story. So let's assume we have one channel, the worst scenario, 10 megahertz on band 48, which is the CBRS band. Then I could define the power. So defining the power, remember indoor small cell are maximum 30 dBm ERP. So I need to check my antenna and what is the gain of the antenna. So it's 6 dBi, meaning I cannot transmit more than 24 dBm. And for the sake of this example, we're just going to match the maximum smartphone transmit power, which is usually 23 dBm. And you have the pattern of the antenna, so you know roughly this is an omni antenna. And we could start. So I'm just going to drop one small cell somewhere, let's say in this big room here. And now I could zoom in and I could go to my antenna contour, right click on it, go to the properties, make sure that I'm using the ray tracing algorithm, which is the more accurate one. And what is my target signal? So if we follow the guideline from Andrew, it was, we're targeting neg 90 to neg 95 RSRP. In RSSI, this will translate to neg 65 roughly. So we're like similar to what we're looking in Wi-Fi. So here I go and I check, I want neg 65. Then I activate my antenna contour. Now I see for neg 65, this is my cell edge. And I see that this small cell is covering well this area. And I just use the clone tool and start cloning that small cell and dropping on other areas. Let's say this area does not really need coverage, it's like mechanical room and stuff like that. And then in the hotel, maybe I need a small cell every other room. And I can see it while I'm dropping the small cells that is actually covering one room and another room next to it. And maybe I could make it every 3 rooms if I want to, like say something like this. And depending on how much coverage I need. So this is giving me an idea of my coverage. And I could move the small cell around if I want a better position, what I need to cover. And you see like the windows, I have like signal coming out here. It's covering outdoor because of this window leakage. So once I'm happy with my small cell positions, maybe I would need another one here on this big room. I can then deactivate the antenna contour and start running some heat maps. So in LTE, you have many heat maps you can do. The most important one, like Andrew was presenting, is the RSRP. So in this case, I want to check the RSRP. I want to combine the system to see everything. And then I'm just going to run that one. And it will show me the RSRP coverage in that floor plan. So the more access points you have, the bigger floor plan you have, the longer it will take to compute the prediction. Now it's calculating all the path, the direct path, line of sight, non-line of sight, reflected path, refracted path, diffracted path, and then combining all this signal into a coverage into every single pixel I have in this floor plan and calculating what is the RSRP value. And it's actually doing it on all floors. So the coverage, even up to floor 4, if I have a small cell here, I would be able to see what's the coverage in that particular floor. And once it's done, then I could activate it. And I see this is my coverage for the entire building and even outdoor coverage. And I could also go to the second floor and see what's the impact of the reflected signal coming from the first floor, reflected up, or the back lobe of the small cell, and even on the third floor. Well, now it's like almost inexistent, but we do have coverage like in the balcony area or something. That's the RSRP, and I could add the legend. So I go to prediction, legend, and I have indoor prediction. Put it somewhere here. And I see what is my coverage, and I could add actually a compliance criteria. And we wanted -95, maybe on 90% of the area. And it will tell me I am not meeting that. I am having 83%, mainly probably because of this area here that we didn't want to cover. But that's basically the RSRP heat map. And the other most important map is the SINAR map. So if I go to SINAR, combine the system again, and again, this is worst case scenario. We only have one channel that we can reuse. Ideal scenario, you would have multiple channels that you could reuse, the same as in Wi-Fi. So this is my channel, my SINAR map. You see when you are close to the small cell itself, the SINAR is good. You see it's like 30 dB or higher. As soon as I get between the small cell, then the SINAR degrade. And it's closer to 8 and then degrade all the way down to 2. I could activate the probe and actually see what is my SINAR here. This is the area where I have like bed. So the ideal situation is to design that this area is actually where nobody will be connecting here. And you see between the rooms, we have bed SINAR. Ideally, I would have 2 separate channels. So I would not have this bed SINAR. So I have one channel here and a separate channel here, so I don't have this overlap here. And same thing here, we could target a minimum SINAR. Let's say my minimum is 20, 90%. And you would see that I'm not meeting that. I'm 55 because I'm using worst case scenario where I only reuse one channel. So that's basically high level design of a CBRS network using LTE. I do have a completed project here where I'm only covering the indoor. I don't care about the outdoor. This is the first floor. And you see we have the outdoor area. If I want, I could run the prediction for outdoor, but here we're focusing on indoor. And if I do the legend here and apply the compliance criteria for the same scenario, like 95, 90%. Now I'm meeting that target because I'm focusing only on the indoor. And I have the coverage on every floor. And I could actually visualize that in 3D with our 3D viewer. So this is the hotel in 3D. And you could see that I have some coverage in the balcony. And then I could switch to wireframe and see the coverage and where are my small cells and what the coverage looks like. I could also go inside the rooms and see exactly what's happening. And I could go like in flight mode and start flying inside the hotel. Go out, I'm in the corridor, and I see my heat maps. And I could go in any room and check what's the coverage inside this room, go to the next room, this small cell should be here somewhere, and so on. So that was a design. What we can do is actually, once this design is completed, implemented, the next step would be to do a survey. And we're glad to announce that we do have a tool for that now. We have our mobile app to do Wi-Fi survey, and now we added the LTE possibility. Like now you could capture the cellular and Wi-Fi in the same time, or you could capture one of the others. So once the project is completed, usually what we do, we save it to the server. So we go save it to the server, and then it's stored on the cloud. Then I'll switch to the phone, and on my mobile app, if I go back, I do have open from server here. So I open project from server, and then it will load. And then I have my project. Let's say I'm on the first floor, and somewhere on the first floor, maybe I'm at the entrance here. And now I could do a survey. So I start a new survey, and you would see now you could select between Wi-Fi, cellular, or both, and you have the option to do stop and go or continuous. Let's say I want to do both Wi-Fi and cellular, and so I don't have to do the survey twice. I can do Wi-Fi, capture it from the least capable, most important device, which could be an Android device, and I could capture whatever this device is seeing in cellular. So I am walking somewhere here. It's going to record both Wi-Fi and cellular, and it's actually telling me here, like, I am seeing this Wi-Fi and I'm seeing this cellular. So this is the LTE, this is the Wi-Fi. And then I continue walking, and once I walk the entire floor, I just hit the check mark here. I do have the pause option if I need to go and annotate something or add any markup. Once I'm done, I hit the check mark, and it will load the survey. So here I have my Wi-Fi 2.45 gigahertz, and I have my LTE. Well, here it was the 3.5 that I designed, but since I'm home, I don't have any CBRS network, but I do have the LTE that my phone was connected to, and this is the data that was recorded. So it identified the operator. Here in Canada, I'm connected to the Rogers network. This is the operator ID, MCC-MNC. I do have the tag, which is the tracking area code, the eNode BID, the cell ID, the PCI, which is basically the small cell ID, and I have the channel bandwidth, channel number, and the downlink. It's possible also to get the uplink. We will add that later. And you have RSSI, RSRP, RSIQ, SINAR, CQI. Not all phones report that value. Only some phones report that. And if I'm doing any active survey, it will tell me what's my downlink and uplink throughput. And if I have many points and if I have the neighbors collected, I would be able to select which channel I want to see, which PCI, and I could switch between RSSI, RSRP, or RSIQ, or even SINAR map. So that's our new product that we are really excited to launch, and it will come in probably a few weeks from now, and I hope you will use it for your CBRS deployment. Thank you very much for attending this lecture, and I hope you guys have any question.
Thanks for that, Djamel. And so to wrap up today, I just want to show you an overview of what the Celona solution looks like. We provide an end-to-end infrastructure solution for private LTE and 5G networks. That includes our Celona RAN, or small cell APs, both indoor and outdoor. They're optimized for LTE and 5G operation. Celona Edge, which is our software-defined private mobile network controller that implements the enterprise packet core and other functions such as spectrum registration with the SAS. Our Celona Orchestrator, which is the management dashboard that is AI-powered and provides a DevOps framework through APIs for automation of the network. And Celona SIMs that are both physical and eSIMs for getting those devices, those client devices, onto your network. So we hope you've enjoyed this presentation today. Please contact us at Celona.io or at iBwave on Twitter. Please visit our website. And we do have a lot of additional information, both technical and non-technical, on CBRS and private LTE and 5G technologies on our YouTube channel. So please go look us up there and reach out if you have any questions. Thank you for attending.
Thank you.